Start.
Start with the picture. Why it's not the poster? This should be the poster.
Actually, I have an intention. You'll see in a couple minutes.
Okay.
Okay, so well, I forgot my name.
So many questions about the poster.
Okay, I'm An, and I have been working here as a front-end developer. And today I'll talk about the topic of how to create your own programming language. And it's actually my bachelor thesis, and I intended to give the presentation here a couple of weeks ago, but the schedule was fully booked, so I already gave it at school. So now this is like the last time that I will give this presentation. Well, first I would like to thank my gold sponsor, who sits over there, for creating this poster. That's why this is like a PowerPoint slide, not a poster. And this is sponsored by him. You know what I mean.
Yeah, the glass is coming down like
Thug life.
Okay, so ignore this title. It has nothing to do with that. Okay, so the goal of this presentation is that at the end of this presentation, you guys will know how to create your own programming language. So first, let's define what is a compiler. A compiler is a software that translates the program written in one language, also known as the source language, to another language called the target language. And the goal of this project is to create a compiler that compiles a procedural, simple programming language called Tiger to x86 assembly. And why do we need a compiler in the first place? First, there are two types of programming languages: the low-level one like assembly, and the higher level one like Java or JavaScript or whatever. But the processor can execute the code in low-level programming language directly, but it does not know how to compile Java or JavaScript like directly. So you need a compiler to translate from high-level programming languages to low-level ones, so that the processor can execute it directly. So that's the reason why we need a compiler. And why do I choose to write the thesis about the compiler? So actually, last year in May, I took an online class about language design. So it analyzed the feature that are in some functional programming language like standard ML, Racket, or in an object-oriented programming language like Ruby. So one of the assignment is to write a interpreter for Lisp language like this with a lot of parentheses, and it confused myself as well. And if you want to take a look at functional programming in general, you can take this class, and I highly recommend it. So the milestone: first, in May, I took that language design course, and then I thought that, okay, it might be cool because I already wrote the interpreter, so maybe it could be easier to do a compiler as well. So I started the project in September 2018. And well, I didn't make that much progress in September and October, so that's why I had to switch back to working part-time to devote some of my times into this project. And it's actually two projects in the end. So at first I read a book and I coded the project according to the instruction in the book. So at first the program was written in standard ML, which is the language that I talked about earlier. And later on, I talked with my supervisor, and he said that, okay, you have to solve some problem with your thesis, and writing a compiler does not solve any problem. So, okay, I thought that, okay, it's cool. Why the hell do you do that to me? And so, okay, so I take a look at some other alternative, and I decided to use framework to create a compiler instead of compiling it, doing like a full stack compiler. So I ported the code from standard ML to OCaml, and because they are in the same ML language family, which includes standard ML, OCaml, F#, and recently Reason ML, which is it is like a new syntax of OCaml. So there's nothing really cool with that. There's no reason to use Reason. And well, and I started writing the report in January and finished it like two months ago. But let's just ignore that. Okay, so for the development process, so how there are several phases in constructing a compiler. Well, you can read it. I won't read it because there are too many of them. And so they can be divided into two parts, front-end compiler and back-end compiler. The responsibility of the front-end compiler is to compile your source language to an intermediate language. And on the contrary, the back-end compiler take the responsibility of compiling from the intermediate language to the assembly. And well, actually in this project, as I said before, the first project is to follow every step from here to there to create a compiler that compiles to MIPS assembly. But then I took the framework called LLVM, and it reduced the scope of compiling from full stack to just front-end compiler. And well, you can see like the shortcut over there. So I'll skip all of those parts, which is the hardest part of the compiler. And okay, so what's next? I don't remember. Okay. Okay, that's it. I learned it yesterday. So first, the first phase of the compiler is scanning, which is also known as lexical analysis, which is like a fancy term. But what it does is that it scans the input file from left to right, from top to bottom. And it does two things. The first thing that it does is to remove all, not remove, but discard all the empty spaces, comment, and like the tab character or the new line characters. And the second responsibility of this phase is to group a sequence of character into a valid token of the language. For example, it groups the I and the F character into the if, and same for Y, for, or anything. So at the end of this this phase, you have like a stream of token without any kind of comments or empty spaces, whatever. So let's take an example. So this like a function declaration in the Tiger programming language. So it starts with the keyword function, and then the name of the function double, and then it takes an argument which is a, and a has the type int, and it returns int. And then in the body of the function we have a and multiply by 2, and there's a comment in between. So let's take a scan. First we detect that it's like a function, then we just ignore the empty spaces here, And next we have a double, and we recognize it as an ID because it's the name of the function, the name of the type, and the name of the variable, which is categorized as ID. And then we have the left parenthesis, and we ignore the empty space again. And then we have an ID as well because it's variable name. Then we have the colon and the integer and so on. So at this point, we just ignore the comment, and then we have the 2, which is a number. So at the end of this phase, you already have like, let's just assume that there is an array of those tokens. So the program does not know about any empty spaces or comments or whatever. So you just leave it out. And
Yeah.
boy! Let's take one.
okay. So at the end of this phase, you have a stream of token, which is ready for the next stage, which is parsing. And the fancy term is syntax analysis. So what we do in this phase is that we take a stream of token and then we match them against some kind of patterns. Here are some patterns that we use to parse the function declaration that I showed in the previous slide. So as you can see here, it's like the function declaration, which has the function token, the ID, the left parenthesis, and it has a kind of special. It's not a token because it can be expandable. And then there is the right parenthesis, the colon, the ID, the equal, and then the expression, which is a multiply expression. And based on these grammar rules, which we call context-free grammar, we match that against the stream of token. So let's take an example. So first we scan for this. We scan the stream of token from left to right, and when we detect a pattern, then we just create a tree node out of that. So let's take a look. First, we discover that this is like the argument section because it matches the pattern that we already declared in the previous slide, and then we scan to the variable a, and we have the expression which has two fields. The first field is the left value, and then the second field is an operator which is a multiply character, and the last field is an integer which is 2. And then when we scan the whole expression, then we detect that this like function declaration, and we create a node function declaration which contains all the information that it has. And from this point, we only operate on a tree data structure, which is this tree. It does not have any leaves and no roots as well. Okay. Nobody left. Okay. So let's go back to how to create your own programming language. So
Yes, call.
that's it. Actually, it's like the end of my presentation already. Now I'll just recap what I have learned. So how to create your own programming language. The first step to do is to download a front-end compiler or insert your language over there. For example, Go, Java, JavaScript, or whatever. The next step is to change a few keywords. You just download the source code and then you navigate to the file that has a configuration. Then you change a few keywords. For example, if you are a native Swedish speaker, then you change the keywords to Swedish. If you are a Finnish or Russian, then you just change the few keywords into your own language. And well, if that does not satisfy you, then what you do next is you change a few grammar rules, but this might be like risky because you might face the problem of conflicts in the grammar rules. And well, at that point, you have to learn something in order to resolve the conflicts, but I advise you to do the second point. Just change a few keywords and then call it your own language. So at the end, you have your own language. No one will argue with you. That is not your own. Because well, you can choose your keyword freely. For example, you can replace if with shit or whatever. So well, I won't go to that, but that's how you do it. And then give a presentation practical about how to create your own programming language. And again? Okay. That's all. Not yet.
So close.
Not yet.
Skål!
I'll torture you guys in 20 minutes. So let's go back to the real technical stuff.
Aw.
So at the end of the previous phase, we have an abstract syntax tree node, which we capture inside a let's imagine this like an object which has several fields. For example, in order to represent the function declaration, we need a name of the function, which is double, and then we have the arguments, which is an array of objects because the arguments can be an array. So it has the name, which is the string, and then the type, which is an integer. And notice that there is a position, which is an integer as well, because at this point you don't have any access to the original input file at all. So you have to capture the original position of some of the declaration or some of the token into the tree, because after that, if you want to throw an informative error for a user, then you use this kind of position in order to display it in an error message. And then we have the result type, which can be optional because function does not always have to have result type. And this the body, which also contains another AST node, I mean the abstract syntax tree node, which is an arithmetic expression. It has the left operation, the operator, the right operation, and then it also has the position in here. So from this point on, we only operate on this type of tree. And so
One
the
question.
yes,
Where does that position come from? How does it?
it's from the original input file. For example, you detect that the keyword function is at the position 6 from the beginning. So you capture that position, and then you just when you pass it, you put it into the
So from the
S
beginning
tree.
of the.
Yeah,
okay.
yes. So the next phase is semantic analysis, and this phase does actually two things. The first thing that it does is, well, in this case, is checking the type of the program. What? Checking types. And the second thing that it does is to check the scope of variable. So I'll explain why that variable declaration in JavaScript was done wrong. Okay, so it has something with checking the scope of the variable. For example, if you want to define a variable in the block of an if or a while, after you escape that block, you can still refer to that variable and get the same value, which is something bad. I don't know if it's the feature or not. So for type checking, what you do is that you use a hash table in order to do the type checking. So for example, you scan the tree, you traverse the tree from top to bottom, and whenever you see a variable declaration, whether it is like an argument variable declaration or it's like a normal variable declaration, you put it into a hash map. and the same for the type as well. So we have the name, we have the table over there, which has the name and the type of the variable or the type. And well, let's see. The next step is that we do the type checking. And so we see, so when we scan to this point, we see the left variable and the left field, and it is like the variable A. And we look into the table and we see that A has the type int. And then we check the operator, which is multiply. So if it is an integer, then we expect the second argument to be an integer as well. And you see it here is like an integer expression. So we can conclude that the body of the function has the type integer, and because the type checked, so it's okay. But what if variable A is like a string? So it could not be multiplied. So in this case, we should throw an error, but in this case, it's okay. And then next we check that the body of the function has a type integer, and we check it against the result type, which is an integer as well. So everything matched correctly. So we say that this program is okay. And the next, the second responsibility of the semantic analysis is to check the scope of the of variable that are declared. So in this case, we also use a hash table in order to check the scope of the variable as well. And what we do is to traverse the tree from the root to the leaf. And we also have the same table again. And in this case, the program here has two lines. The first line is the function declaration, and when you see the semicolon at the end of the first line, is like the end of the body of the function. So on the second line, the variable A should not be used in the second line, and we should throw an error after that. Well, we can do that by using this table. So when we evaluating the body of the function double, we already have this table by scanning the nodes, and then we see that when we see variable A, we know that it's already in the table, so it's okay. So it's the first line is fine, but the second line, what we should do is that we should check the table again, and in this case, variable A is only available in the body of function double, so it should not be used on the second on the second line, because what we should do is to remove it from the table before we exit the first line. And so there's nothing in the table, and we do the lookup for variable A on the second line, and we don't find it at all. So we should throw an error and flip the table. So this is where functional programming comes in handy. You have the function composition for pizza. So it's like pineapple on top of the pizza, or pizza on top of the pineapple. It's like function composition. And enemy of the state. Well, let's just go back and I'll explain like why it is handy using immutable data structure in here. So as you see in the table here, when you enter a scope of variable, you put it in an imperative way. You use a hash table, which is mutable. Then when you are evaluating the body of the double function, you add the variable into a hash table. And when you exit the body of the function double, you have to remove the variable A from the table. And normally people do that by using a stack. So when they enter a new scope, they just put a marker on the stack, and then they put a lot of variable allocated in that scope. On the top of the marker, and when they exit a scope, they just discard all the variable on top of the marker, and then they also remove the marker, so that when they evaluate the second line here, the variable a is no longer in the hash table. But doing that might be a bit, well, you have to code to do that. But if you use an immutable data structure, for example, let's imagine when you enter the scope of the body of the function double, you use a immutable data structure like a map, which is well, at that point you have a map, and when you add a variable a to the map, you just create a new environment hash table, not really hash table, but it's like a map. So and you keep the instance of that variable for evaluating other subsequent expression. But when you exit the scope of the body of the function double, then you still have the immutable map in the beginning, which only has the type double, I mean the name double and the type in integer, return integer. So at that point, you don't really have to manually remove the variable out of the hash table. Well, let's just move on.
Oh,
So you guys might wonder, why do we introduce like another intermediate representation language in between? Why don't we just compile from the language to assembly directly? Well, you can do that, but it's not reusable, so I'll explain. So each type of processor requires one specific type of assembly. For example, the Intel processor requires the different type of assembly than the one that the ARM has. So it's like, if you want to compile from one language directly to an assembly, you have to do one direct translation, and you can see the example here. So if I want to compile from Java to Phantom, and I want to compile from Java to MIPS, then you have to do each translation separately, and the same for ML and Pascal and C and C++. So at the end, you ended up having 20 translation, which is a lot. And well, it doesn't have to be that way if you use a common language in between. So if you use and translate an intermediate language in between, for example, if you want to translate Java to one language, and then you translate from that language to other architectures, like for architecture on the right side. So you can do that at first, and then for ML you can do like the same thing over again. So at the end you only have to do 9 translation, which is a huge reduction over 20 translation. So that's why we introduced the concept of an intermediate language. So normally the intermediate language is lower level than the source language, but it's higher level than the target language. So let's just go on.
You're almost out of beer. Do you want another one?
No, I have that.
Skål!
School. So one of the most popular IR at the moment is LLVM. So if you are an Apple fanboy, then you probably heard about this. But
So good.
it's okay.
Never heard about it.
Oh no, he's right over there.
Well, how can you?
This guy. You can only see the app.
But yeah. Well, what it is like a set of components that can be composed and used in order to create a compiler in a very timely manner. And it is created by the creator of the Swift programming language, Chris Ladner. So he created this framework in 2003 when he did the master thesis at some university. So
I
after
like his
that,
credentials.
after that he was hired directly by Apple in order to create a Clang compiler for their tool chains. So the Clang compiler is the front end compiler on top of LLVM, and it compiles the C language family like C, C++, Objective-C to LLVM, and then from LLVM it compiles to assembly. And it is shipped in Xcode 3.1 as far as I remember. So nowadays, well, if you use Apple products, then probably they are LLVM running in behind. And as you can see, why do I use it? Because it's trendy and it's well tested, developed, and optimized. And we can actually call the C function directly from the language that I compiled, that I create the compiler for. And it is used in many languages like C, well, of course, the Clang compilers. And then it is used in Swift, which actually use two types of intermediate representation. So Swift actually have one intermediate representation language on top of LLVM, and then from that language it compiles to LLVM, and at the end it compiles to assembly. And in Rust, in Haskell, and WebAssembly, and Kotlin native, which is well, Kotlin is a JVM language, and Kotlin native is a project that compile Kotlin to assembly. So how do I do that? How do I use the LLVM compiler? Actually, LLVM is a set of tools, and I only use 2 or 3 tools. What time is it? Okay, I'll speed up. So I write the compiler to compile Tiger language to LLVM IR, and then after that I use several provided tool by LLVM to compile from LLVM IR to binary code. And it's LLC and Clang. LLC is a static compiler that compiles LLVM IR to the binary. And for Clang, I use Clang in order to integrate the language, the Tiger language, to some function written in C. So for example, if you want to do print instruction or a random statement or anything, so you write it in C, and then you compile it to LLVM IR, and then you link it to the language that you create. So LLVM IR, what it is?
Skull.
Okay, thank you. So LLVM IR is a abstract. You can think about it like an abstracted assembly version. So it's a bit lower level than C, but higher level than assembly, and it's not processor dependent like assembly. So you see it shortly. So this is the factorial function written in the Tiger program, and the equivalent version of LLVM IR programs are shown on the right side. So the LLVM IR module has several functions, and in each function you do the control flow using blocks. So at the beginning of the block, there is a label, for example, the entry, then the else, and the merge in this case. And at the end of each block, there is one conditional branching, which is like a jumping around block, depends on some kind of condition, or unconditional jump like in the then and the else block. So actually in LLVM IR, there is no syntactic sugar for the while loop, the for loop, the if, the else, whatever. So you implement the control flow by using block and then jump between the blocks using some kind of condition. For example, if you want to create a loop, you create one test block in order to evaluate the condition, and then there's one loop block. So if the condition is true, then it jumps to the loop, and at the end of the loop, you jump back to the test in order to test the condition again. And if it's false, then you jump to the end block, which execute other instruction not in the loop. So I'll talk briefly about the backend compiler. What it does is that it maps the IR instruction into assembly, and then the second part is to allocate the memory for variables in the program. And then the third thing, the third responsibility is to optimize the generated code. And I'll skip every optimization here. Okay, here. And LLVM IR static compiler, which is the static compiler that compiles LLVM IR to assembly. And what is it about? So first I compile the Tiger program into LLVM IR using my own compiler. And then after that, when I have the LLVM IR, I use the optimization in order to optimize it. And then after that, when we have the optimized version of LLVM, we compile it to assembly using the LLC. And after that, you kind of link to some function that are written in C using Clang. And after that, you generate a demo, the executable file. And what I learned in this project, first, like some kind of functional programming, which I don't use that often and I won't use.
Ever.
So it's nice to know, but well, I think it's not really, it's not my type. So it's nice to know about it, but I don't have to necessarily use that because it's not natural to me anyway. So I learned standard ML, OCaml, and recently Scala. And then I learned something about compiler design, and then I learned some really low stuff like assembly, and at the end is LLVM. So there are a few lessons that I have during my my process of doing this project. So first is that the lexing and parsing are the first two parts of the constructing process of the compiler. So at first I dig really deep into that and learn the algorithm and whatever, but at the end I think it doesn't matter because there are tools out there for you to do that. For example, when you define the token of the language, you just use regular expression, and for the parsing, you just need to define a set of grammar rules in order to do that. So there's no need to dig really deeper into that because, well, it doesn't matter in the end, you use the tool anyway. So it's nice to know that how it works, and when it doesn't work, then you know what to do. But in general, I think I spent like 1 month for that, and I realized that it's such a waste of time. Then LLVM is really nice intermediate representation at the moment because it's widely used, and if you want to create a compiler in a very short amount of time, then I would advise you using LLVM. Actually, you can use some kind of intermediate representation like Java bitcode or the .NET intermediate representation as well. But I think LLVM is kind of nice, and C is like it's the simple language in a sense that there are not so many features, and you can actually drop in the code to the C function using LLVM, and it could save you the years of optimization, and which that is actually hardest part of writing the compiler, which is the backend. And if you use this framework, then it will take care of that automatically for you. And if you want to generate some kind of codes that LLVM supports, like if I want to compile my language to WebAssembly, to Rust, to assembly in general, then you can do that in theory. But in practice, when I try to compile this language to JavaScript, I installed the tool, but then the Golang compiler was broken, so I just removed the tool and just be happy with that. But in theory, it's possible. So this is the chip. Don't care about this part. My favorite scene in Forrest Gump. Okay, let's move on. Okay, so I would like to do a live coding as well to introduce the language.
Score.
I ran out of beer.
I asked
Which
you
is
if you
such a
wanted
shame.
more.
I'll take more. But how many minutes do I have left?
Well,
Well, it doesn't really matter at this point.
What time is it?
It's like
5:20.
Oh.
It's 1 hour.
Okay,
after
I'll do
4:20.
like the quick coding section in a few minutes.
Right. How many minutes? 2?
5 minutes maximum.
But hold on.
If I don't have any bugs.
Hold on. Maybe we should have Jan
Yeah.
talking numbers.
Oh, okay.
Janne talks numbers.
Okay. Sorry.
No, don't be sorry.
Okay.
Yeah, it's.
Okay.
You do
Let's
it.
do it this way. Jan
can
is
have-
gonna talk about numbers.
Yeah,
takes
alright.
about 90 seconds.
Yeah.
No.
And then
It
you
will be like-
be fast.
I'll copy and paste.
Nice.
That's
Great
the way.
demo.
That's
Like
the
the
way.
real people. Man, I love this like view. This looks
Try to
Super
plug
HD.
this one in. The HDMI part. Yeah.
Okay.
Yeah. There you go.
Alright.
bland.
So is it there yet?
Whoa, okay.
Okay. Then open and code. First I'll
This is-
create a
This is the
file.
view we want. Yeah, this is ghetto. Nice.
First zoom in. Yeah.
I have to zoom in.
Yeah. Shift plus.
Not that there.
Yeah. There you go.
You added some pluses in your name.
That's fine.
Okay, so I'll create a file. So let's do a let's write a small program that look through every element of an array and apply some kind of aggregation on top of that. So let's call it reduce function. And in here there are well, first we have to define the program. So we need to define a variable. So this is the let expression, which has 2 parts. The first part is a variable declaration, and the second part is a result expression, which you can see in some languages like Clojure or standard ML. So let's define a result type. I mean the result. So what we want is to print out the result. So I'll use a C function, which I gave an alias. So it prints an integer. And what we do here is that we call a function reduce with the array, which is xx, and then the function, which is a sum, and then the initial value, which is 0. And in here we have to define the array, the sum function, and the reduce function. So let's define an array. So we use the keyword var xs, and we assign it a value. So let's create a type of in array, which take the size of the array, which is 4, for example, or 4, which is the last 4 is a initial value of the of every element of the array when in initialization, and well, we have to define the type of the integer array, which is an array of integer, and then we have to define the sum function, which we define by using sum. Then we need an accumulator, which is an integer, and then a value which is x, an integer as well. And we have to define the type of the function that returns. So it is an integer, and we use x plus x. So the next thing that we the next thing that we have to do is define a reduce function, which take an array and then look through every element of an array and apply the sum over each element of the array. So let's define function reduce, which take in an array, so s, which is an integer array, and then the next argument would be a function, and we have to define the type of the function. So it's type function in fun equal then the type of the argument integer, and return type is an integer. So the type of function f has the type integer fun, and then the initial value, which is an integer, and then we want to return an integer as well. So let's define the body of the function reduce. So in here we have to look through every element of the array, and we could do that using a for loop or a while loop, but let's just avoid mutation and use recursion. So in order to do that, I'll define a helper function with the let expression in n. So in the let expression, I will call a helper function g with the well, we start at the end of the array, so the index should be array length of the xs, and then we have to minus 1 because it's the last index of the array. And for the function g, we define a function g, and then the argument would be an integer, so it would be like an integer, and it should return an integer, and this is like a recursive function. So we have to define the base case. So we start at the end of the array, so we have to stop at the base case, which is an index 0 or index minus 1. So let's define it in if the current index is minus 1, then we return an initial value, and if not, then we call, what should we do in this case? Okay, we call the function f, and the first argument of function f, which is an accumulator, so it is a computation of the previous index, so it should be g with the index n minus 1, and then the second index, the second argument would be the current element of the array at the index n, so it should be at x, and then should be n in here. Hopefully this is correct. If it's not, then I'll just escape. Okay, let's see if it works. So you have to use a script in order to compute it. Let's see if it works. Array length has not been declared. Okay, I'll see an example. Just a moment. It should be array length, not array length. Okay. Okay, so let's see.
So is array length is a predefined function in
it's
your
a predefined function.
Tiger language?
Well, it's a C function actually. So in order to define an array, in low-level language, you use some kind of one way to put it is that the length of the array is put on the first element of the array. So if you have like 4 elements in the array, then you put the 4, which is the length, into the first element of the array. So if user access the index, which is out of the length, then you should throw an exception at that point. So you have to save the array data and then the length of the array at the same spot. So as you can see, the result is 16. So let's do a the multiply function, which multiplies every element of the array. So it be function multiply, which take the first argument, which is an integer, the x, an integer, then an integer, and then you apply the multiplication into this, and let's call it another function. Print out the result. Is multiply, and because it's multiply, then the first argument, the initial value should be n. It should be 1 instead of 0, because if it is 0, then everything will just return 0. And let's see if it is correct.
Yeah. Sorry.
Well, it seems to be correct. So let's try to change one element of the array. For example, an array. Let's change the 5th element of the array. Let's see if it throws an error. So hs minus it should be this way, like 4. Let's see what it does. Hopefully it throws an error. Well, it throws an error, array outbound. So let's change it to the second argument and change this one to 5. So let's see the result. So it's this result, and that's all I have to say. That's it.
So yeah, boy. So the semicolon is not really mandatory, but it's just for.
Well, it's
separating
actually
line.
mandatory if you have a bunch of expression in the body of the let. But in the from the first part of the let is like variable declaration. So it is either type declaration, function declaration, or normal variable declaration. So normally you separate them by the keyword at the beginning. So if you can see like type var function, but in here in the body of the let expression, you have to define some kind of separation in order to distinguish between lines. So it's actually like a simple language, and have you can have a look at a generated code. Well, the generated, this is like the assembly. No, this is the generated code of the function that we have just do. And one of the hardest feature is the function closure, because it generates tons of unnecessary code. This is not the optimized version. But yeah, it's still quite like verbose, and well, nobody write this kind of code, so it's just like a generated code. And this like a assembly.
Yeah.
And
brings out some memories from Bloom. Yeah, Bloomquist. God damn it.
Yep.
I got 1 from that course.
I got 5.
Yeah, because you copied from someone else, of course.
Okay,
Well, I
so
did.
that's all I have to say, and that's it.
So you got 1. Very nice.
It was beautiful.
Thank you.
Beautiful. Everyone was beautiful. Very nice.
That was actually a really interesting project you have there.
Yeah, I think it's pretty interesting, and well, it's not really useful, but maybe sometime in the future.
You learn the like internals of
Yeah.
like any programming language
Yeah.
will be turned into assembly anyway.
Yeah,
So it's
and
like
the cool thing about using like the same intermediate representation is that if you want to copy a feature of some language, you just generate the same code and then you copy it. Okay.
I think that's going to be everything for this week's Beer and Banter. See you next Week.
Okay.
Like and subscribe.